In part 2 of section 8.1, we're going to look at factorial notation. So factorial notation, it looks like we're really excited about numbers because we have a number with an exclamation point after it, but that just translates to in factorial or 7 factorial. We don't just say 7, like we're super excited about the number 7. So for in factorial, it just means you take that number and multiply it times all of the descending numbers after it all the way down to 1. Okay, so when I have 5 factorial, I'm going to do 5 times 4 times 3 times 2 times 1. That's 5 factorial. When I do that calculation, we end up with 120. So 5 factorial equals 120. Okay, it's a shorthand way to show that kind of computation. So if I'm going to evaluate 7 factorial, we're going to get 7 times 6 times 5 times 4 times 3 times 2 times 1. If you think about it, 5 factorial was 120. So we're essentially taking that and multiplying that times 6 and times 7. When we do that, we get 5,040. Okay? Then, when we are asked to write the first 4 terms of the sequence a sub n equals n plus 1 factorial over n, well, let me show you what's going to happen. We're first going to take 1, and we get 1 plus 1 factorial over 1 factorial. Okay, so that's going to be 2 factorial over 1 factorial. Well, 2 factorial is 2 times 1, which is 2, and 1 factorial is 1. So that equals 2. Okay, when I do a sub 2, we get 2 plus 1 factorial over 2 factorial. Well, that's going to be 3 factorial. Let's think about what that is. 3 times 2 times 1 over 2 times 1. These cancel. All that's left is a 3. So if we keep doing this, we're going to notice that a sub 3 is going to be equal to 4. And a sub 4 is going to be equal to 5. It's because the factorial, the n plus 1 factorial over n factorial, all that's going to be left is that n plus 1 value. Because if you think about it, n plus 1 factorial is the same thing as having n plus 1 times n factorial. So if I have that over n factorial, that n factorial cancels out, leaving me just with n plus 1, which is kind of cool to see. And you'll see a couple questions in your homework that relate to that. Okay, so using summation notation. So instead of writing out the individual sums of the terms, we can actually write it in a shorthand way. So we use this Greek letter, which is a sigma, and we have how it's going to be evaluated or how the terms are evaluated. And we have what's called a tracker or a tracer where we start from. So this k equals 1 is my starting value or my starting term. And then this top number is your ending value or your ending term value. Okay? So we say that k is the index of summation. Some people call it a tracer or a tracker. 1 is the lower limit and 18 is the upper limit. So I use kind of layman's terms to describe those things, but these are the official terms. So we can expand and evaluate each sum. So this one here, we have the sum of 2k to the second, where k starts at 1 and it ends at 6. So what that means is we're going to take 2 times 1 to the second. That's my first term in the sum. And we're going to keep going 1, 2, 3, 4, 5 until we get to 6. 2 times 2 to the second, plus 2 times 3 to the second, plus 2 times 4 to the second, plus 2 times 5 to the second, plus 2 times 6 to the second. And when we sum all of those together, we get that it is equal to 182. Okay, so This is a shorthand way to show that we're going to sum up each of those terms in the index that we're summing, and we can solve and actually get a numerical answer. Okay, so here we have our index of summation is I in this case. So my terms are 2 to the 3, because my starting point is at a 3, minus 3, plus 2 to the 4 minus 3, plus 2 to the 5 minus 3, and that's my stopping place. Okay, so I'm going to do each of these. And when we sum each of those terms together, we get 47. This last one looks tricky because we do have an index, but we don't have something that's being evaluated. Our term is just 4 every single time. So my first term, my k equals 1 term is just equal to 4. K equals 2, I get a 4. K equals 3, I get a 4. K equals 4, I get a 4. K equals 5, I get a 4. So when I add those all up together, 1, 2, 3, 4, 5, 5 times 4 is 20. Okay, so that's what happens when we have that this notation where there's not something to be evaluated in. Each term is just for itself. Okay, now we're going to work in reverse. We're given a sum, and we're going to write that sum in summation notation. So first thing I want to look at is what is the thing that is changing each time. The base changes each time and increases by 1, but the exponent stays constant each time. So what's changing is my base. So I'm going to call this n, and the exponent every single time is a 3. So that's not going to change. Now to show how my index is changing, well, we're starting from 1, okay, and then we're ending at 7. So my ending value is 7. And this is the summation notation that matches that sum. We're going to do the same thing down here. Now, if I look at what's happening, essentially this first term right here is the same thing as 1 over 1. And then this is 1 over 2. And then this is 1 over 2 squared. So let's think about this. This is 2 to the 0 is the same thing as 1. 2 to the 1, 2 to the 2. 8 is 2 to the 3. And then we're going to go all the way to 1 over 2 to the n minus 1. So that is my ending value in my index, and my starting value is 0. So the sum, starting from, let's use I this time, I equals 0, going all the way up to n minus 1. Okay, so we could pick a value, but in this case we write it as n minus 1, of 1 over 2 to the I. Okay, so this is the summation notation for this sum right here. And lastly, we're going to consider this sequence a sub n equals 1 plus 1 over n to the nth power, and they want us to find a sub 10, a sub 100, a sub 1000, a sub 10,000, and a sub 100,000. When you complete the computations on each one of these, and so I did it shorthand, I kind of used video magic to write them all out, so you didn't have to see me compute each one of them. I just used my calculator to do so. You get, for a sub 10, we get 2.5937, etc. For a sub 100, we get 2.7048, etc. And we keep going and going. And when we get a sub 100,000, we get 2.71826, etc. And if you were to look at the number e, this is getting really approximately close to that. So if you look at the definition of what is the number e, you're going to see something that looks a lot like this. And if you're more curious about it, send me an email. We can discuss it. All right, thank you.